Good morning, students. Today, in this maybe small discussion, we shall prove that homeomorphic image of a normal space is normal. Okay, we need this small result to get a counter example for the fact that subspace of a normal space need not be normal, as well as product of normal space need not be normal in general. Homeomorphic image of a normal space is normal. It means that suppose there are topology spaces x and y, okay, and a homeomorphism f from x to y, and x is normal, then y is also normal. Y is also normal. That is, if you are having a homeomorphism from a topology space x into y, in which if you assume x is normal, then y is also a normal space. Okay. As a consequence of this result, we can say that the concept of normal space, okay, is actually a topological property. That is, it is invariant under homeomorphism. Okay. It carries every normal space into a normal space. Okay. For the proof, we assume x and y are two topological spaces. Okay. And f is a homeomorphism from x to y, and further we assume x is normal. We shall prove that y is also a normal space. Y is also a normal space. So consider an arbitrary point a in y. Okay. Consider the singleton A. We need to verify that whether every singleton set is closed in y or not. Since your f is a homeomorphism, okay, basically it is a 1-1 onto map, and f is continuous and its inverse is also continuous, or in another word, f is an open map, okay, as well as f is a closed map. Now singleton A, now it's a subset of y. It's a subset of y. You consider f inverse of singleton A. F inverse of singleton A. Okay. F is a bijective map, therefore this is, okay, only a singleton set. Otherwise, this may be a subset of x which contains more than one point. Okay. Now f is a bijective map will imply that its inverse, f inverse of singleton A is a unique point in x, say D, and therefore we are having f inverse of the singleton A as singleton B. Now this is actually subset of x. This is actually subset of x. So singleton B now consider as a subset of x, where x is a normal space, is closed. This is closed in x. This is closed in x. Okay. Now again, we are using the fact that f is a closed map. That is, f carries every closed set into closed set because it is a homeomorphism. Okay. Therefore, f of singleton B is closed in y. But f of B is actually f of f inverse of A. That is our singleton A. As here again we are using the fact that f is a bijective map. That f of singleton B is closed in y, which means your singleton A is closed in y. That is our A. Okay, we have chosen arbitrary point A in y, and now we prove that singleton A is closed in y. So the first condition for the space y to be the normal is verified now. Okay. Now you take arbitrarily two closed sets A and B which are disjoint in y. Okay. You assume A and B are closed in y. A and B are closed in y, such that A intersection B is equal to empty. So we are considering two disjoint closed sets in Y. We need to prove that these two closed sets can be separated by means of design open sets. Okay, that is, we need to find U an open set, V an open set in Y. Okay, U containing the set A, V containing the set B, such that U intersection V is empty. So we need to prove that. We need to prove that result. A and B are closed in Y and F is homeomorphic, therefore F is continuous. You have this one, F inverse of A, F inverse of B as closed sets in X, because F is basically a continuous map. So fullback of every closed set is closed. Therefore F inverse of A and F inverse of B are now closed in X. Closed in X. Okay, they are closed sets in X. And also they are disjoint. They are disjoint. Intersection is empty. Why? Because if you are having a common point, say Z is a common to this as well as this, then F of Z is a point of A, and because Z is assumed to be a point in this set also, F of Z is in B. Therefore your A intersection B is non-empty, which is not possible, because the basic assumption on A and B is they are disjoint. Therefore you can say that there is no common point among these two sets, F inverse of A and F inverse of B. Therefore these two are disjoint closed sets in X, such that disjoint also. Okay. Now look at that, X is a normal space in which you are having two disjoint closed sets. Therefore by definition there are open sets, say U1 in X and V1 in X, such that U1 intersection V1 is equal to empty, and U1 containing the set F inverse of A and V1 containing the set F inverse of B. Okay. That means F inverse of A and F inverse of B can be separated by means of disjoint open sets in X. Now it is quite easy to write this line. F of F inverse of A is contained in F of U1. F of F inverse of B is contained in F of V1. You take this as U, this as B. Now again we are going to use the property that F is a homeomorphism. Okay. Here U1 is open in X, therefore F of U1 is open in Y, therefore U is open in Y. Similarly, V1 is open in X, F of V1 is open in Y, therefore capital V is open in Y. Okay. U and V are open sets in Y. Not only that, by the bijective nature of F, this becomes your A and this becomes your B. Okay. So U and V are open sets in Y. One contains the set A and another contains the set B. Okay. Also U1 intersection V1 is empty, will say that U intersection B is also empty. Why? Suppose you are having a point common to U and V. Suppose Z belongs to F of U1 as well as F of V1. Then what happen? This Z can be written as F of small U1 for some U1 in U, for some U1 in capital U1, and similarly Z is also a member of F of V1. Therefore the same point can be written as F of V1 for some V1 in capital V. Okay. Now here what you get is F of V1 is equal to F of V1, but F is a one-on map basically. Therefore U1 must be is equal to V1. So this implies U1 must be is equal to V1, where U1 is a point of capital U1 and V1 is a point of capital V1, which means that U1 and V1 have a common point. Okay. You get a contradiction to this fact. U1 intersection V1 is empty. They are disjoint. Therefore these two sets, capital U and capital V, are disjoint. Okay. That's all. What we have proved for arbitrary closures in Y, disjoint closures in Y, we have proved that there are open sets U and V in Y, U containing A and V containing B, such that U intersection V is empty. Okay, that's the requirement, the second requirement for the space Y to be a normal space. Okay, summarize, we have already established that every singleton set is closed in Y. Now we prove that for every pair of disjoint closed sets in Y, there are disjoint neighborhoods containing A and B respectively. Therefore, the space Y becomes a normal space, which completes the proof that homeomorphic image of a normal space is normal. I hope you understand this result. Thank you.